profound speaker, Dr. Sarika Jain from NIT Kurukshetra. Now, before handing over the session to Dr. Sarika, I would like to give a brief introduction of her. Dr. Sarika Jain graduated from Jawaharlal Nehru University in 2001. Her doctorate, awarded in 2011, is in the field of knowledge representation in artificial intelligence. She has served in the field of education for over 19 years and is currently in service at the National Institute of Technology, Kurukshetra. Dr. Jain has authored or co-authored over 150 publications, including books. Her current research interests are knowledge management and analytics, the semantic web, ontological engineering, and intelligent systems. Dr. Jain has supervised two doctoral scholars who are now pursuing their postdoctoral studies, one in Spain and the other in Germany. She has been PI of sponsored research projects funded by CSIR TechWeb 3 and the Defense Research and Development Organization India. She works in collaboration with various researchers across the globe, including in Germany, Austria, Australia, Malaysia, Spain, USA, and Romania. She is a senior member of IEEE, member of ACM, and a life member of CSI. We welcome you, ma'am. We are really glad that you spared your valuable time from your busy schedule. We can start, ma'am.
Yeah, thank you so much, Dr. Deepthi. You have read the profile so nicely. Okay,
Thank you,
let us
ma'am.
continue with this. I hope that the participants will appreciate this new topic, that is knowledge management. And I don't know how many of the may I ask how the participants will like to query the session. Will they like to do it at the end? And otherwise, I am okay if you,
Yes.
yeah.
Yeah, ma'am, they will be posting their queries in the chat window towards the end of the session.
Okay. So, dear participants, if you people really feel that there is something disturbing you and there is a problem you have to ask in on the way only, then you can always unmute your mic and ask me. That will never be a problem. So, you could ask. May I ask the participants before starting the session that have you heard of the term semantic technologies? Have you heard of knowledge management, and how is knowledge management different from data management, that is DBMS? If any participant want to speak something, I like to know that the participants are working in which field. So anybody can unmute the mic and say.
Participants, you can write in the chat window.
And
And if
they
you,
can unmute themselves also.
Yeah, you people
okay,
can
okay.
unmute
Then they can
yourself also
answer
if you
now.
want. Otherwise, please write in the chat window yes or no. Either you have listened about what are semantic technologies. I speak some more keywords: RDF, OWL, Sparkle, SWRL, ontology, vocabularies. Have you heard of these terms? If you have really heard of these terms, please say a yes. Because this session is all about this, and a very interesting topic that is to be used for digital forensics. So I do not find a yes in the chat window. This is what I also thought that this will be the case, and I hope all of you are unaware of the topic, that is semantic technologies and knowledge management. Okay, so I've also tried my best to keep the session very introductory so that we will not dwell ourselves into the details. Okay, so let us go ahead. The title is knowledge management in digital forensics. So, as Dr. Deepthi has already introduced, I am Sarika Jain from NIT Kurukshetra, and my talk today revolves around how to manage the knowledge in digital forensics field, the cyber crime and all. So, how to manage the knowledge is the topic of today. The agenda of the session will be: I'll discuss the problem space first of all for digital forensics, then a shift from data management to knowledge management and why is it necessary, semantic technologies and knowledge management, and how to manage the knowledge in digital forensics.
Sarika ma'am, you are not audible.
Yeah, now I think,
Yes, ma'am, you are audible.
yeah. So the agenda of the session continued as RDF as the semantic data model. Then how do we apply these semantic technologies to the digital forensics, and certain key takeaways at the end of the session. A list of selected bibliography. So let us start with the problem space of digital forensics. You can see the technological advancements are always increasing the occurrence of computer crime. Terrorism is there, cyber crime is there, that is the worms and the viruses, the cyber crime. Then child pornography is there, that is the illegal use of computers. That is true that the technological advancements are impacting and also accelerating the computer crime, but they are also providing a solution to it, like digital investigations guarantee a legal use of these technologies, as well as they allow us to capture, store and analyze the evidences. The technological advancements provide with us better visualization of data for digital investigations and also facilitate the automatic generation of knowledge. So this is perfectly fine, but the problem comes when we have more tools, when we have more devices, when we have more data, and that is the problem of today. That is the global data is exploding. The number of devices are increasing. So we are facing the problem of interoperability as a major problem in today's date. So for the problem space also, have a look here. This is the digital crime scene of today, and the forensic requirements are trustworthiness is a major forensic requirement because data integrity and the process reliability plays an important role, because it is not a it is I should say a high risk area, and the life of the criminal that is put to stake. So efficiency is also a major requirement, the speed and high return on the labor invested, because in today's date most of the digital forensics are done manually. So this digital forensic investigation process is largely manual in nature. That is why it requires a highly skilled labor force and also time. The available tools have limited capabilities of integration, because the evidence sources are multiple and they are even distributed across the cloud. The forensics have requirements of trustworthiness, that is very, very important. All these challenges have worsened, and they are worsened in the increasingly computerized environment, because the today's environment is highly networked. That is why the challenges are worsened by themselves. You can see here that because of this highly networked environment, we have large volumes of data. There are several evidence data sources and they are highly distributed. There is variety of data formats and protocols. The processes are even manual. Complex time consuming tasks and legal requirements are there. All these problems we need to tackle, and this big amount of data is majorly providing the interoperability problem, because the data itself is very heterogeneous in nature. So how to come across this, how to solve these problems? Before coming to the research questions, in fact, let us look at the major challenges which are related to knowledge management, in fact, or I should say now data management, and later on we'll come to knowledge management. So the challenges are, first of all, yes, there is scalability, that is the increasing number of devices are there, users are more, interactions are more, and the interactions are not simple, they are getting more in volume as well as velocity. So you need to be scalable, you need to find scalable solutions. Device and data interoperability is a major problem because of the diversity and heterogeneity of the enabling devices, because of the multimodality of data, hard disk, memory, mobile devices, there are security logs you have, then the network traffic. Next problem is unstructured forensic data. Yes, it is highly unstructured, because it is coming, most of the forensic data may come from social media sites also, and it is in the police records also. So it is highly unstructured, and there is lack of support because existing digital forensic tools have limited capabilities of integration from multiple evidence sources. So we are having a lack of support. The data is very dynamic and unreliable. It may be noisy and incomplete also, because the data of forensics is never complete. It is time and location dependent. The generation of a unified timeline of events from multiple sources present different time zone references also. There are different timestamp interpretations. There can be the clock drift also. So the data quality becomes a major issue. Out of these five issues that I have just discussed, these five challenges, the cover up challenge comes the semantic gap. The data captured is very low level in nature, as you all know, and it is highly unstructured. So there exists a semantic gap between the smart spaces and the higher level concepts that users are interested. The machine is interested in the low level concepts. It understands the digital only zeros and ones, while the user is providing the higher level concepts. And also there is a lack of standard vocabulary, because when multiple parties are involved in the analysis process, there is lack of an agreed set of terms and definitions, which may create problems. So given this array of problems, I have framed a few research questions related to the data and the knowledge management. They are automating the analysis phase. You need to, because it is highly manual in today's date, so we need to automate the analysis phase of the digital investigations in the highly networked environments. You require uniform representation and integration of the multiple diverse evidence sources. You need to enable the automated correlation, a simple reasoning and querying procedure also you need to enable. So all these, if done, will facilitate the knowledge management process. So let us go through how we'll be able to do this knowledge management. First of all, let us understand why are we shifting from data management to knowledge management. As you all know that it's all about data, and the global data is exploding. IDC is a premier global provider of market intelligence and advisory services also. This company IDC helps the IT professionals make fact based decisions on technology purchases. So this chart I have brought from the IDC global data sphere analysis, that is the annual size of the global data sphere. IDC has predicted that more than 59 zettabytes of data will be created and consumed in the world this year in 2020. As you can see here, in 2020, more than 59 zettabytes of data will be created and consumed also. So this global data sphere will grow from this 59 zettabytes this year in 2020 to near about 175 zettabytes around 2025. So IDC predicts that since the same data is being processed again and again, so it is driving the unique data sphere down to 10%. Have a look here. In today's date, the ratio of unique data to replicated data is 1:9, while by 2024, it is predicted to be 1:10. So this driving down of the unique data sphere by 10% of the total data sphere is to be taken care of. So I say that there exists a gap. There is a gap between the potential and the delivered value. There is a gap between the data and the actionable insights you derive from that data. The actionable insights and the value. There exists a gap between the original data and the insights you are able to derive from that data. Even a recent study conducted by Forrester for HP Enterprise surveyed around 5,000, more than 5,000 machine learning practitioners, and it was found that only 14% of those practitioners had a very defined, a repeatable, and even a scalable process to operationalize their ML models that had delivered a range of demonstrable projects. And more than 86% of companies have yet to formalize the process, and they're struggling to operationalize their ML models. Why is it so? Because whatever data they are able to put up in their data stores, they are not able to derive proper actionable insights. They are not able to derive value from that data. Even the the situation gets worsened, because say they have a lot quantity of available data. Now the amount of data they are able to analyze is less. if they are able to analyze that data, then even the amount of data that they are able to put to operation is less. And this all data also includes the data that is the proof of concept stage. So this all is so surprising, as because it is already 7 years from when we entered the age of analytics 3.0. In 2013 we entered the age of analytics. It is 7 years from 2013 till date, and till now it is more than 86% of the companies have yet to formalize their ML models because they are not able to operationalize it. When I say operationalize, let us say what I mean by saying that, because in today's date, all of us have the Hadoop solutions, the Hadoop cloud solutions also. So we are able to put more and more data under management. You can see this black curve. So this black curve is the total data that we have in today's date, say, or that we are able to store using the Hadoop solutions. But look at the blue curve, that is the analyzed data, because all the stored data is not analyzed. So this is creating an inside gap, that is the blue curve. All the data is not being analyzed. Again, look at the dashed curve. This is the operationalized data, because all the analyzed data cannot be put to operation. So the execution gap comes in. This execution gap is the gap between an organization's ability to analyze and make sense and its ability to apply it in some operational setting. So we call it the so-called operationalization problem. We abbreviate as O16N. So we have to work towards that. Whatever data we have, we should be able to analyze it, and after analyzing, it should be put to operation also. So how do we do that? There is a shift from data to knowledge. There is a shift from data management to knowledge management. The DIKW pyramid, since long we hear about this DIKW pyramid, but till date we are working with data only. We are not able to reach I, K or W, that is intelligence, knowledge or wisdom. What is data? Data refers to the raw facts, symbols, numbers, online sensors, or unstructured or structured, whatever. All form of data, when it is raw, we call it data. And you know nothing about data. You cannot get the insights from this data. Now, when this data is put to certain context, we say that we have the information now, because context and value add meaning to the data. For example, say I say any term, I say that it is 2007 2020. It doesn't make sense to anyone, but in the context of date, we say that it is 20th July 2020. So it gets a meaning and it becomes information when we say that these numbers represent a date. Another example can be a telephone service providing telephone numbers on request. Now, when the telephone service provides those telephone numbers on request, now it has become information for us. Then comes knowledge. When put to experience, when with your experience you are able to utilize that information, it becomes knowledge. For example, in the child's mind or in human being's mind, you get some information, you accumulate it in your mind, and it becomes knowledge which you can use at any point of time you desire. So how when the information that is derived from this collective data becomes relevant to our goals, the pieces of this information connect together through relationships to add more meaning and value, and it can then be applied to achieve our goal. The rules, when we encounter relationships that are not explicitly stated, then we get knowledge. For example, we have something in our mind, we have three facts A, B and C, and using those three facts we are able to derive some fact D which is implicit, which has not been explicitly stated into the information. We say that this fact number D is knowledge, it is not information, because using our experience or certain set of rules that we have devised for ourselves, we are able to attain that knowledge. So now what we are doing is, in addition to defining the relationships, We are understanding the patterns. We are looking for rules inside those facts, and we are able to derive some knowledge which is implicit in the information. So your information is now explicit. Whatever was implicit has come to explicit now, and you have clear awareness of the facts, and you know exactly the how of everything. If I take the example of the table of two, so understanding now, because after knowledge it comes understanding. Understanding is some form of stored knowledge. For example, the table of two. When understanding is added, the student can answer all the difficult multiplication problems like 790 into 45. If we ask him if we ask him 790 into 22, the student is not able to answer immediately. But if he understands the table of two, and if he understands how the multiplication problem works, we say that he has understanding and he has attained that wisdom. So I repeat, knowledge is something memorizing if it goes back to our long term memory. Understanding is learning it, that is synthesizing new knowledge from the old knowledge. An example of wisdom is the ancient preachings or the ancient sayings. And we can say that the today's computers do not have that understanding, so they do not have that wisdom, understanding the principles, that is acting using the knowledge, because the computers are not able to derive the actionable insights by themselves. We say that they do not attain wisdom for now. And human are the most are the animal having the highest level of wisdom. For example, you look here in this chart here, you see going down, the meaning is decreasing, the applicability is decreasing, and when you go up, all of these increase, and to a level, to a value which is equivalent to human. Going upwards towards the wisdom is what will happen, or you are looking into the future, while going down you say what has already happened, or you are looking back into the past. So we are moving from data management to knowledge management. We are moving from, people in today's date speak about data science, they speak about data analytics, but in this session I want to emphasize on knowledge science and the knowledge analytics. We need to climb up the mountain of wisdom, and semantic technologies, I introduced the term semantic technologies, make it possible by how by creating links between the heterogeneous data sources. Semantic technologies allow us to create links between the heterogeneous data sources. Let us see how we are able to do that. So if we define what is knowledge management, data management, I hope all of you are aware of what is data management, what is information management. As we do it today, the today's RDBMS stores, most of the participants here also might be using the SQL stores or MySQL, Oracle, some DBMS. All of you might have used in your work, in your projects, but we are not working, we will not work on DBMS, that is the database management. I want to emphasize working for the knowledge management and the knowledge stores as compared to the relational data stores. So how do we define a knowledge management? This is the definition from Wikipedia. Knowledge management is the process of creating, sharing, using, and managing the knowledge and information of an organization. It refers to a multidisciplinary approach to achieve organizational objectives by making the best use of knowledge. So, we emphasize on knowledge. What is in fact knowledge management, and how does it differ from the information management? Let us have a look on that also in the next slide. First of all, define knowledge more properly. Knowledge management is a discipline for the systematic management of the knowledge assets with the goal of capturing the insights and better understanding. As I said, we are moving up the pyramid so that you have better understanding for meeting the tactical as well as the strategic requirements. So we are not working only on the operational requirements. In fact, the strategic requirements are also tackled, that is you achieve wisdom. So the certain, let us look on certain issues which are involved. So there are two types of knowledge types, as I said, implicit and explicit. Explicit knowledge is the knowledge which is codified, that is the information in data, the codified knowledge found in the databases or documents. While implicit knowledge, that is the tacit knowledge, is the experience based knowledge, the context dependent knowledge that you derive insights after the reasoning over the explicit knowledge. Next issue is representation. We have to look into representation, that is providing the high level descriptions of the word that can effectively be used by the computer. We need to provide a representation that is understandable by both, by human also and by machine also. Then comes storage, that is storing the knowledge. As the data is stored, we need to store the knowledge also. And reasoning, that is processing, that is finding the implicit consequences, finding the tacit knowledge, that is the context dependent knowledge, from the explicitly represented knowledge. So we'll look on all these aspects, that is representation, storage and reasoning of knowledge as compared to data, because I focus on knowledge management. Have a look very quickly on this slide, that is the difference between information management and knowledge management. I hope it is already clear to the participants. Information management is the practice of collecting and managing and distributing the information. So I emphasize this is information. It's about the physical collection and organization of the hard data, but not the opinions and intuition. Why I say not the opinion and intuition means the implicit knowledge is not made explicit. While when we talk of knowledge management, it is the process of doing, capturing and effectively using the knowledge. It's about how people learn and validate the shared knowledge. So it manages what? Data and information, while the knowledge management manages structured information, understanding and also wisdom. Information management has rigid, limited capabilities of the traditional relational database. We'll look at some of the drawbacks also of the traditional relational database, while the knowledge management has a fluid pool of standardized data elements. We'll see just now what are those standardized data elements. Information management centers on processes, while knowledge management centers on people, means it is more context dependent. We have here emphasis on explicit characteristics only, that is the facts and figures of hard data, while in knowledge management we look for both the tacit and the explicit characteristics. Here we measure the knowledge, the information can only be measured quantitatively and in short time frames, while here in knowledge it is measured by the changes in the behavior and also the work of the individuals and teams over the time frame. Information is useful, but it is very easy to replicate, so there is no uniqueness, while knowledge leads to innovations which are unique to the company, because based on the different context you can have different meanings for the same thing, thereby it is providing the competitive advantage. In information management, you know what only, that is the facts, numbers and stats, while in knowledge management you also know that how you have attained it, that is the action, experience and innovation is there. So as you might have heard of the explainable AI, in today's date people are working with explainable AI because mostly the machine learning and the deep learning algorithms are not able to derive how they do very good tasks. They say they may say to a person which is maybe asymptomatic to a disease, the DL algorithm can very beautifully speak that this person has a very deadly disease, say cancer, but the human being will not believe till he comes to know how do you deduce, how do I take an action. So this is because the DL depends upon the facts, statistics and figures, that is it knows only what, because it rely on information management and not knowledge management. Here comes the difference, that is I told when I showed the challenges that the wrap up challenge is the semantic gap. because we have this semantic gap. That is why all these problems are arising. So the semantic technologies are helping as the enabler. Let us see what do I mean when I say semantics. And different users have different interpretations for the same vocabulary. Syntax describes the correct format. Semantics describe the required comprehension and the correct interpretation. So, what is semantics? It is words, that is symbols, plus accumulated knowledge and context also. So, there exists a semantic gap. And closing this semantic gap means to define the intentions of each model type by the description of the modeling method to apply. I repeat, how do we close this semantic gap? Because the semantics are missing in information management. How do we close this semantic gap? Closing the semantic gap means we have to define the intention of the model. Means to which context we need to put this model. We have to define the intentions of the model type. How? By the description of the modeling method that we need to apply. Have a look here on this example. How human perceive an apple. This is the high level feature. A human has an image of an apple in hand, while the machine looks it in the form of low level features, that is zeros and ones. The encoding, resolution, color and texture, everything is in the form of zeros and ones. There exists a semantic gap in the human perception and the machine perception. There is a semantic gap and we need to resolve, we need to close this semantic gap. That is why I recommend moving from data and information management to knowledge management. And the same problem is for digital forensics also. For digital forensics also, we need to fill the semantic gap and we need to move to a perception where human also is understanding the same code and machine also is understanding the same code. Let us see how. So I said that these semantic technologies are acting as an enabler to fill the semantic gap. The semantic technologies are to be utilized as the kernel technologies to overcome all the challenges I listed for the data management. So you can see here, there is a time span from 1988 to 2014, because till 2014, most of the semantic technologies already got standardized. From 1988, we had Unicode, HTTP, HTML. So in this time span, you can see the at the bottom the foundation technologies, starting from the simple web technologies, Unicode, HTTP, HTML as the foundation technologies. Then came you can see this URI in 1998, then IRI in 2005. Why? To have a unique reference identifier for everything, for every concept around the world or your domain also, you have URI. Then we switch to IRI to have the international characterization. After foundation technologies, as you go up, you can see the various serialization standards starting from XML as the serialization format. Then there is go up, there is data model RDF. In the later slides, we will look at the difference also from XML to RDF. Actually, as we are moving up in this ladder, you can see we are moving from foundation technologies to the ontologies as the top. We are getting better expressiveness in thoughts. Whatever we are representing, they are better expressive. So if you talk of XML or you talk of RDF, you say it is getting better expressive. And if you go up, then you use RDFS, that is schema language of RDF. What is RDF? It is the resource description framework. And we say that instead of, for example, till date, maybe on the web, people use XML as a smart exchange format as compared to HTML. Previously, we used to use HTML because the browser understands only HTML. Then we start having, there was a problem in exchanging the code. So we started using XML as the serialization format. And in XML, we have semantic markup, we have semantic tags. But those semantic tags, again, human is not able to understand. Human can understand, but the machine is not able to understand the meaning of those tags. For example, people, company, we put those tags in XML for human understanding, but machine still is not able to understand. That is why came RDF data model. We will go in details for all these things. Then there are other standard syntax and serialization formats. You can see here JSON. Then for the embedded metadata in the code itself, you have others like RDFA, micro formats, micro data is there. Then from JSON, we have JSON LD. JSON LD means linked data. Now your JSON format is changed in syntax and structure so that it is able to link to other open data standards that are available on cloud. Then there is turtle, there is n triples, and many serialization formats. Such formats are available, and RDF also can be serialized in any of these formats. Then came the NoSQL revolution. You might have heard of the NoSQL databases, MongoDB, Cassandra. Even Facebook started using the NoSQL databases because of the drawbacks of RDBMS. People switched to NoSQL revolution. I will like my participants to interact at this point of time. If you people have heard of NoSQL revolution, please tell me some languages or some databases, some NoSQL stores, and what was that major problem in RDBMS stores that the research community and even the industry switched to the NoSQL. Anybody from the audience, anybody from the participants, please come ahead and try to interact, try to tell me. You can Google it also so that the learning increase. Please tell me why we started the NoSQL stores. How many different types of NoSQL stores are there, and why we started working with NoSQL. You can unmute your mic, or you can write in the chat window. You can Google the answer which I am asking. Can you hear me? Majorly, we use NoSQL store because of the ACID restrictions of RDBMS. Right? Okay. So we move to NoSQL from RDBMS, and even we are able to draw the graphs for NoSQL stores. Again, there are certain problems, that is ACID properties are not there in NoSQL. So later on from NoSQL also, we have moved to knowledge graphs. We have moved to semantic technologies. From the semantic web, we started with it. Come to the last layer, that is the topmost layer, with ontologies plus inference, that is the languages. So you have RDF schema, RML, OWL, DML plus OWL, SWRL for the rules, that is the rule language. Then Sparkle is there for query, and all the versions of it are listed here. So you can see here in this chart also, as the cost of operation, even the syntactic flexibility is increasing as you go down, but as you go up, the effectiveness increase, the efficiency increase. You have more semantics, you are more expressive. When you use RDFS, you are more expressive. When you use RDF, you are less expressive, and so on. But yes, definitely nothing comes free of cost. So the computational complexity increases, but you have better reasoning capability. So moving forward with using semantic technologies as the enabler, have a look. I've already briefed all these in brief in the previous slide itself. Let us look at some of the differences. Why not to use XML as for data exchange, and why not to use RDB for the data store? As XML is very widely used, I've already told that you add semantic markup to XML, But computers do not have that intuition what those tag names mean. Even the DTTs and XML schema are able to specify the structure of documents, but not the meaning. So XML, I say, lacks a semantic model. It only has a surface model, that is a tree model, but it lacks the semantics, and there is a semantic gap. Even you want to be more machine readable and machine interpretable. That is why the XML representations are making no commitment on the ontological vocabulary. You can use any word with any meaning at any point of time. You can use the tag people to label a book even. You can use the tag book to label a people even. So it is not committing to any domain specific vocabulary. So which word shall be used to describe a given set of concepts is not defined. XML representation requires pre-agreement to the vocabulary. You cannot change the schema. Once you have written people for some type of concepts, then you have to use people again for every such concept. So XML representation is feasible in closed collaboration only, and for the agents which are in a small world and a stable community only, not for the shareable web resources. Have a look here on a sample XML representation. This is from a lecture by Barnaghi in Internet of Things. So look here, this is the Celsius temperature. It is 15 Celsius temperature recorded at time 8:15, and this location, the longitude, latitude. Now this is XML representation. So you see decimal value, C unit, but the machine doesn't understand that it is unit C, that is the Celsius. So now we have the RDF representation, and you can see it is in the form of a graph. You have measurement in between, and all these units as relationships, we provide meaning to the computer, and they now understand what does it mean. Means has value, means this is the value. And again, the unit, we say has unit, we have defined that this is the unit to the machine. So through this RDF graphical representation, the machine is able to represent that through this link, it is reaching to some unit of this measurement. And this is the schema, and in the below diagram, you can see one particular instance of that schema, that is 15 Celsius. I've committed a mistake here. It should be C instead of Celsius, that is XSD string. So if we look at the machine representation of this RDF graph, that is how do we code this RDF? You can see there are certain tags which are already defined actually, and they conform to a predefined schema. So it is committing to some ontology, I should say. You see here has value 15. So has value is already known, means this 15 is the value, this C is the unit, this 8:15 is the time, and machine also understands it now. So RDF is a semantic data model that is machine understandable and machine interpretable. And RDF triple includes three things. We call it a triple: a subject, predicate, and an object. And a set of certain triples is referred to as RDF graph. You can see this is a RDF graph with triples like measurement has value decimal, measurement has value 15. These are the triples, and all these triples collectively are making the RDF graph. For example, you see the triple, say you have some digital forensic evidence, evidence 3 is of RDF type file. Evidence 3 is contained in disk 2. It means that it states the fact that a particular evidence with ID evidence 3 is of type file, and the same evidence 3 has been acquired from a disk which has the ID disk 2. So RDBs are used for the discrete data problems, while RDF graphs are used for the connected data, because you are able to make the graphs. So does human mind think in terms of relational database? No, of course not. It's much easier to pass information between our heads and a graph than just creating the weird database models. And for example, if the machine, my connection got lost, I think.
Yes, ma'am. But now you are audible, ma'am.
Okay, I'm audible. So I need to share my screen.
Yes, ma'am. You have to share it again.
Okay, so will any participant let me know where I was when I lost the connection?
Ma'am, the first,
Did I describe this?
yes, ma'am, you had started with this. Ma'am, all this we have gone through.
Okay, okay, fine. So I'll go ahead from
Yes, ma'am.
here.
Right, ma'am. Right.
Yeah, right. So what I was telling is that human mind doesn't think in terms of what RDBMS look in terms of tables, because it's much easier to pass information between our heads and the graph that is creating, because the database models are very weird, I should say. So it is hold on. Okay. So, all of you might have worked with relational databases, and you know the process. How do we reach to tables? First of all, we need to make the entity relationship diagram, ERD, and then only we switch to tables. So if our machine can understand entity relationship diagram, then what is the use of writing the tables? And understanding those entity relationship diagrams will always be much better than writing the tables. So this is the emphasis to use graphs, the RDF graphs, because tables are made only for machine understanding. If machines could have understood ERDs easily, directly, that's why we are here with the RDF graphs. The global data is very unstructured. It is real time, massive, high velocity data, and it is coming from different locations. It is having multiple formats, and all these problems can be easily tackled with what I call as the RDF data model, because RDF is a semantic data model as compared to the existing data stores. These RDF graphs provide us a platform to reveal complex relationships between unrelated data sets. For example, you have a RDB, and there you have a single valued attribute. So you convert it to 1NF, and you convert that multi-valued attribute to single valued making use of the first normal form. But say at some later point of time, that single valued attribute again becomes multi-valued. So what to do? In relational databases, how you do that? You delete the complete column for that attribute, and you create an entirely new table which is holding all the multiple values for that attribute. And you need to have a foreign key reference also. Perfectly fine. Okay, we will do that. Just we need to do it, but it is time consuming. All the indices that you have already created with the original table will get invalidated. Even the SQL queries which you have already run on the previous table gets invalidated. While in contrast, the RDF graph model is incremental in nature. And now the data scientists can focus on solving the problems instead of ending up with just dealing with and cleaning the data. And all these databases, Enzo, Allograph, Neo4j, Virtuoso, we call them knowledge bases, because they connects to the data lake and creates a graph automatically. Have a look here on this beautiful picture from the Neo4j NoSQL store. They are having, say, the data store at 6 different places. You can see the purchases data on the left, then product catalogs, views, and so on. But logically, whenever some real-time query comes in from the upper level, that is the applications and systems, the data is queried, and On the fly, knowledge graph is created that is connecting all the different data stores through relationships. You can see that this knowledge graph on the way in between, you can see in this rectangle, this knowledge graph is providing a 360-degree view of one entity and its surrounding entities also and all the relationships. In addition to providing answers to the queries, they are even capable of explaining how they have reached to that answer. To have a better view of what are knowledge graphs and how do we use it, say we are searching for Tim Berners-Lee in the Google search, then what it does is it fetches value from the different data sets, the linked open data cloud data sets, DBpedia and Wikidata. For example, in this case, it fetches the value from Wikidata about his brother, about his house, and from DBpedia it fetches information about his both the wives, that is Nancy Carlson and Rosemary Lake, that he has two children, and it combines all the data from both the data sets, prepares a knowledge graph, and now it is easier for the query to get better answers because it is combining the data from all the different data lakes. So it is able to provide the search results or recommendations, or even it can be put to some another application, whatever is required. So knowledge graphs build a rich user experience. How? By combining knowledge regarding the input keyword from multiple sources. So here is a recommendation to use RDF data model for the uniform representation. As we started with the research question, for this uniform representation of the digital forensics data, we recommend to use RDF data model and the semantic web knowledge graphs for the integration of multiple diverse evidence sources, and this way we will be able to solve that research question. Look, from various devices you can have data in different formats, say it is CSV, even the data store SQL, JSON, XML. You need to transform the data, integrate it, and using NLP techniques you fetch the data. You need to put it into a knowledge graph, the all data in some data store or a knowledge store like Allegro Graph, Enzo, Neo4j, some NoSQL store, some graph store. You need to put this knowledge graph using some knowledge graph embedding. Then whatever algorithms you put this knowledge graph to, finally you are able to develop some intelligent applications, semantic search, knowledge analytics, or whatever. Now, how to create a common schema? As I told, in XML it was a problem that say you use people, you can use the term people either to represent a person or a book or a computer or anything. The machine doesn't create any problem. But now what we say, whatever knowledge graphs you are creating, whatever RDF graphs you are creating, these RDF graphs, if they conform to some schema, then it is always better because that will be a common tag name to all the entities in the graph. So how to create a common schema model to make sure that the same common tag will be used among different parties. The highest level of expressiveness, that is ontologies, help us addressing this issue. Have a look here on certain examples of knowledge graphs. Google, the top shot, uses knowledge graphs, and Google is the one who has introduced knowledge graphs for his semantic search. For example, here you can see the entity search and summarizations, that is the semantic search. This search for Michael Jackson will do not show you the web pages, but it will show you the structured knowledge by virtue of, you can see the info boxes on the right hand side. So you are able to discover the related entities. Even, for example, have a look here, you are able to discover the different related entities to, if you say Michael Jackson's music albums, then you search, when you search for Michael Jackson's music albums, you are able to look for all the related entities which are related to Michael Jackson albums before looking for the search result, the static search result, that is the web pages on the bottom. You can see one has started. Similarly, you can get the factual question answering from the Google Knowledge Graphs. When you say an exact total question, what is the date of birth of Michael Jackson, you get the answer 29th August 1958 directly in a search window, and you do not need to look into the documents to search for that. The LinkedIn is using the economic graph. Look at some of the examples from the industry. It is an example from Minerva Intelligence. They posted in June 2020 even. It is a private company focusing on bringing the benefits of AI to the mining industry. You just see here on the right hand side that the airborne magnetic survey imagery as the raster imagery, they have fetched these images, and then they are doing the signal to symbol transformation. That is, they're perceiving those signals and converting into symbols, so that some ML algorithms could be used, some DL algorithms could be used to classify. Now, where is the beauty of semantic technologies? Look here, more sophisticated ML algorithms will be able to label those lines of the imagery. Very good. But the semantic alignment is required, and the semantics are fetched from the books, from the literature. That is the terminologies and ontologies for making it for making the semantic tagging of those imagery. You require these ontologies, terminology, or even we used to use the term semantic networks when we read our AI books. So the logic programming and some reasoning with uncertainty is also possible when you uh, annotate your symbols with the semantic markup. And finally, you are able to conclude with the advices and explanation. So the emphasis is on embedding human knowledge in machines, and human knowledge, yes, resides in literature. So we need to embed those ontologies so that you are able to do the semantic markup and remove the semantic gap. Next example is the COVID-19 epidemic. Many researchers are working in this direction. This is the graphs for good 2020 ontology to link the various different heterogeneous data sets about COVID-19. This is a very beautiful example, the CSO classifier. It is an ontology driven detection of research topics, and the Springer publisher is using this for the smart topic miner project. You can see in the image the architecture, the various research papers you could input to the system, and the system will tag the research papers based upon whether this research paper is of machine learning, semantic web, about ontologies, or IoT or big data. So it is able to classify your input research papers with various tags. How it is able to do? Look at the table on the right hand side. Even it is performing better. Look, the last one, that is the CSO classifier in the end. That precision, yes, it is suffering. The STM module is getting the best precision, but the CSO classifier has the best recall. This is because it is using the background knowledge, the CSO ontology, and the graphs it is using. So it is getting the best F1 measure, that is 74.1% F measure. This CSO classifier is being used by Springer for its smart topic miner project. In AIoT also, that is artificial intelligence of things, semantic technologies have found its place. HyperCat is a standard for representing the IoT data coming from the various heterogeneous devices, and this data of HyperCat Data Hub is stored in relational databases. So how to enrich this HyperCat Data Hub with semantics. So these authors have developed an ontology for it, and also a Sparkle SQL endpoint for it to query the data. This is also a very beautiful example of the utilization of semantic technologies in intelligent systems. On the left hand side, you can see they are doing the contextual modeling, and after modeling the data contextually, that is using the word to vec model, and the different dimension corpus, means not only one ontology, not only one corpus they are using, they are making it context sensitive, and they are getting the data, they are distributing it into three or many based upon the context that is there. Means the traditional, because the traditional representation approaches may fail to capture the nuances in the semantic meanings. That is why you have the embedding models, that is word to word, glob, bert and all. If we take an example of the social media post by Islamic extremists and the Islamic non-extremists, that is the moderates, both of them reflect different contextual dimensions. So based upon their context, you could model a corpus, and using the word to vec model or any other knowledge graph embedding model, you could separate the data into different contexts. And there is always ambiguity in meaning in terms like jihad has different meaning for Islamic extremists or the Islamic moderates. So different representations are generated through these embedding models, and they're created based on the dimension specific corpora. And how do we use it in your model? Well, after the contextual modeling, you have got the knowledge infused learning module. From the knowledge graph as the background knowledge, you can see here the knowledge graph is being fed as the background knowledge to the neural network model with the various hidden layers also. So using this knowledge graph as the background knowledge as in human mind, you could get you could overcome the obstacles like lack of quality training data. So the knowledge graphs will encode the knowledge, the poor interpretability and all. The idea is to infuse the necessary conceptual information into machine learning architectures. So you need to infuse the conceptual information which you are getting from the knowledge graphs into your ML architectures. It will just boost your recall, and even without affecting the precision. So these knowledge graphs are represented in vector or matrix form using various knowledge graph embedding models. Will not go deep in those embedding models. If I come to digital forensics as a domain for semantic technologies, then many XML based approaches exist. These are two the best people use. One is the digital forensics XML, another is the digital evidence exchange format. So the standardized XML vocabulary, DFXML, is a standardized XML vocabulary for representing metadata to describe the evidences, so that you are able to exchange them using the XML tags, providing various intuitive forensic related XML tags. For example, source of that evidence, volume, partition, creators, and many more. Similarly, DEX is the digital evidence exchange format. It can wrap the output from various tools in an XML based representation. Now we have various even RDF based approaches also. The advanced forensic format AFF is a file format and container to store digital evidence. You have four, that is forensics for rich events. It is a forensic ontology which serves for the tag naming. It is a generic event log parser, and also a custom defined rule language FR3 is used. You can see in this diagram for four, you see from various log files, maybe it can be from the packet, the data image file, the log file. You have the evidence manager. From the various different sources, you collect the data. Then there is semantic parser based upon certain domain ontology. You collect the data, and after collecting the data from the evidence manager, you tag that data, you annotate that data using the semantic parser and some evidence domain ontology at the background. And now you have the semantically annotated data in hand. So you do the inference, that is the SWRL rule engine may work, or Hermit or Palette or any other reasoner may work. And so you need to integrate these ontologies, and later on you could have various, you could run Sparkle queries over the data that is fetched. So you have digital forensics which are knowledge driven now. So I emphasize on being knowledge driven as compared to data driven. Look at the bottom on the this is a common digital investigation process. The digital investigation life cycle is starting from digital evidence, then you acquire the digital evidence, acquisition, then the digital investigators sit in between and you analyze it, finally you report it. So acquisition, analysis and reporting, there are the three major phases. And we map, when we map it with the semantic technologies, we say we work in 4 layers. At the bottommost, using the foundation technologies, we have the knowledge layer. That is, we try to represent the evidence in the form of knowledge using OWL2 or the RDF data model. Then you need to integrate all those heterogeneous data sources using RDF. Then you perform reasoning over it, and then you can always, reasoning is performed to derive the implicit knowledge, and later on you can always query your data using Sparkle. For the reasoner also, you can have various different reasoners. You can have an ontology reasoner, or you can have a rule based reasoner also, that using SWRL language or any other rule language. For collecting the digital evidence, even you see, you are converting the unstructured digital evidences in any format using the domain ontologies at background into RDF, that is the structured representation. And when I say knowledge driven digital forensics, it doesn't mean that you want to forego the existing tools. No, we will work with the existing tools like Sleuthkit for to extract the data from storage, Wireshark for the network traffic, and the forensic toolkit FTK for the disk images. We use all those, but later on we want to convert it in all the data into RDF using some background ontology, a uniform structured representation we have as the knowledge layer, so that you are able to integrate all those different RDF from the different data lakes. And to complement the well-established approaches like FTK, with we want to complement these approaches with the knowledge-driven techniques. And this reasoning layer, in fact, leverages rules in the SWRL format. And the purpose being to integrate different sources of knowledge into a knowledge base, which is including all the different types of evidence from any possible source. Again, there is an example. The title is Ontologies for Social Media Digital Evidence, because much of the digital evidence can also be from the social media. You need to fetch it, and yes, the social media data will again have a new format. So these authors have devised an ontology with these three major terms in the ontology, and every term having certain different subset of terms. There is person, online social network, then there is criminal case, and then there is the crime solving. And this resulting data is now enriched with the RDF assertions. How? Let us see. So from these three, this bigger ontology is made. You can see all the different terms which are related to digital evidence are there in this ontology. Now, how to use it? You are able to classify the information the police has obtained from the online social networks for the wanted profiles, and also the information which the police has obtained from the witnesses of a crime scene. So you can very easily classify that information, because now it is represented in a uniform format. So using any ML model or DL model, you could classify that information in a much easier manner. So the point here is to say that now you are able to form a unified, a linked graph of data, which is representing the multiple evidence sources as one integrated corpus. There is another example from Amato et al. And the very latest one from 2020. You see here in this architecture, the evidence manager in more detail. The document processing is done, event log processing is done, and the data can come from any format. Later on, semantic parser is there. You are integrating the ontology from the public as well as the ad hoc ontologies. You annotate the data, that is the evidences, and put them in any triple store. Any triple store, any graph store can be used for this. For this triple store, in parallel, you could have inference engine or SWRL rule engine, as I just said. For inference, you can use any reasoner. It can be Palette, Hermit, Fact++. There are many reasoners available. Similarly, for rules, you have SWRL rule engine or any other rule language you could use. All these inferences and reasoning will be able to generate the implicit knowledge, which is again put into the triple store, and later on you could have sparkle queries to provide situation awareness to the police, and they are able to use to do better knowledge analytics. Have a look here. This is from PEPS et al 2020. You look here again, the layering is the same. You have the common interfaces for all the data from various different sources. Then you do text and data mining, and heterogeneous data mining and evidence collection as the bottommost layer after the common interfaces. Then you do advanced semantic reasoning, and both types of reasoning you can do inferencing or rule engine, and later on you could get the augmented intelligence. Why? What is the reason of doing this? To get a code proof evidence. You store the code proof evidence in a common representation model and knowledge bases. This is the common representation model, and an ontology. You store it in the form of an ontological instances, or you call it instance box also. So you have the person fusion tool and you have the reasoning tool. These authors have used database for the knowledge store. For the triple store, they have used Apache Gina Fuseke triple store. For modeling, they have used OWL because it is having the best expressivity as compared to RDFS. For serialization, RDF XML they have used, and for rule language, SWRL has been utilized. Yes, I've come to an end of my slides, and this is also a very beautiful example I will like to put forward. Uh, Again, data collection, semantic representation, then reasoning and query. So data collection is the acquisition of evidence, the digital evidence sources from disk images, memory dumps, network traffic logs as a raw format. In forensically sound manner, you collect the data. No matter how you collect it, from where you collect it, you just collect it at one place. Then you represent it semantically. This raw acquired data is passed and represented in RDF, and it should conform to some ontology and saved as a single file. Then you perform ontology reasoning and rule-based reasoning repeatedly. The OWL reasoner infers new implicit relationships and save them in the same triple store you might have chosen. Similarly, rule-based reasoning you have rule languages which identify more complex relationships which might have left from the ontological reasoner, like relating entities from various different sources, and this cycle keeps going. Later on, your triple store has been populated, and now you could have integrated query, that is the sparkle query, over those triple stores with query the uniformly integrated and enriched digital evidence data set. So now this resulting data is enriched with RDF assertions from the prior reasoning phases, and they form a unified graph, linked graph again, and you are able to represent this data graphically, the multiple evidence source, and into one integrated corpus, and you are able to query that corpus now. Again, a more detailed manner, these different use cases and examples I have brought in front of you to motivate the participants to work in this direction, because digital forensics has a lot of scope, because in today's date it is more of manual process. You see, there is log extraction, that is that evidence collection. We sometimes call it RDFization also, because you are converting into RDF. Then you understand the patterns in that triple store, that is the event extraction. using some background knowledge, using some ontologies as vocabularies. Then event streaming you could do, and you could store it and query it for the forensic analysis and for monitoring purposes also. For log acquisition, these authors have used FileBeat. For log extraction, they have used Logstash. For artifacization, they have used Triple Wave. For event extraction, C-Sprite. For background knowledge, they have used Sepsis Cybersecurity Knowledge Graph. And for storing the data, they have used the Virtuoso Triple Store. And through their Sparkle endpoint only, they have done the query and visualization. Here are a certain key takeaways that semantic technologies should become a crucial component for every data scientist toolbox for aiding the knowledge management. The key here is that we are not looking for possible answers, but we are seeking an answer. And looking means to hope for, that we are hoping for something, while seeking means that we have already done our hard work for that. So we are not now hoping for an answer, but we are now seeking for an answer. So these are certain key terms you could note down also, so that if you really find an interest in this field, then you can use it for digital forensics. Here is a list of bibliography that I have used for preparing these slides. And thank you so much, such a patient audience. Any questions and comments are most welcome.